A heavy airplane takes off down the field. The pilot moves a small lever, and up comes that sturdy landing gear, smoothly and easily. A slight pressure and a ponderous tank answers the rein like a well-trained horse. Power under control. Swift, sure, exact control. Controlled with hydraulics. Here is an isohydraulic control system, one of the most modern methods of precision control. The cylinder is absolute slave to the master cylinder and will move in exact step with it. In this picture, we will be concerned with the principles that make such systems possible. That is, basic hydraulics. And now let's see what this hydraulic force is. Let's see what physical laws are involved, how mechanical advantages are gained, how a simple system works, and how it is applied to some of our present-day needs. Many years ago, a French scientist named Pascal discovered that because of the relative incompressibility of liquids, pressure exerted anywhere on a confined liquid is transmitted undiminished throughout the interior of the confining vessel. Keeping this principle in mind, if the pressure is increased, this increase is applied undiminished to every part of the enclosing vessel. If the pressure is lessened, the pressure becomes less to the same extent on every part of the vessel. Almost every hydraulic system has at least three basic parts: a pump to move the fluid under pressure, a pipe to transmit the fluid under pressure from one place to another, and a device, usually a cylinder, to transform the movement of the fluid under pressure into useful work. Great mechanical advantages may be efficiently obtained with hydraulics. In order to explain mechanical advantage, let's start with a pump and a cylinder of equal size, and for the sake of simplicity, disregard line losses and flow characteristics. According to Pascal's principle, every square inch of the interior of the system will be under the same pressure, and as the pistons are equal in area, the total pressure on each will be the same. If the pump is moved, the piston in the cylinder will move with the same force as that applied to the pump, and both will travel the same distance. Now let's make the cylinder larger so that the area of its piston is, say, 10 times that of the pump, and move the piston in the pump. The piston in the cylinder will move with a force equal to 10 times the force applied to the pump, because 10 times the area is subjected to the same pressure per square inch. The mechanical advantage is in direct ratio of the areas of the pistons. However, in order to gain the advantage in force, the piston in the pump must move further than the piston in the cylinder. The smaller piston has to move a distance in inverse ratio to the areas of the pistons. In our illustration, it would move 10 times as far. To move the piston the full length of the cylinder and retain the same advantage in force would require a very long pump. Since this is not always practical, some type of continuous supply pump must be introduced. Here is a hand pump of the type most commonly used on aircraft. Although light in weight and compact, this pump will do heavy work efficiently. As the handle of the pump is moved forward, the fluid in the front chamber is forced out into the pressure line. At the same time, a new supply of fluid is drawn from the reservoir into the rear chamber. On the return stroke, the fluid in the rear chamber is forced through a valve in the piston into the front chamber. The front chamber has only 1/2 the capacity of the rear one, so that half of this fluid is forced on out into the system. The cycle is repeated to supply a continuous flow of fluid under pressure to the cylinder. And now we can drive the piston the full length of the cylinder. We can also cause the piston to work in the opposite direction by adding a pipeline to the other end of the cylinder. This is a modern cylinder of the two-way type. It is capable of performing work equivalent to that of an electric motor of this size, with much greater speed in response, but with only a fraction as much weight. The pressure on the fluid in one end of the cylinder causes the piston to move. This movement forces the fluid out of the other end. The force on the piston depends upon the pressure generated by the pump and the area of the piston. The speed of the piston depends upon the capacity of the pump and the volume of the cylinder. To control the direction and distance of the movement of the piston in the cylinder, a selector valve is used. Valves of the poppet type have generally proved the most successful. Through simplicity of design and precision manufacturing, they are light and compact, yet still capable of performing heavy work. The selector valve directs the fluid under pressure to either end of the cylinder. At the same time, it permits the return of the fluid from the other end to the reservoir. The pressure line from the pump leads into the selector valve at the top. The return line to the reservoir leads out of the bottom. The lines to the cylinder come out of the sides. Moving the handle of the valve one way first opens the return poppet from one end of the cylinder and then opens the pressure poppet to the other end. Moving the handle the other way reverses the order and causes the piston to move in the opposite direction. A relief valve, usually of the spring-loaded type, is installed between the pressure line from the pump and the return line to the reservoir to permit continuous operation of the pump. This valve permits the return of the fluid to the reservoir. And now a power-driven pump can be added as a source of energy for the hydraulic system. The most widely used power-driven pump involves only 2 gears and is very simple. A hand pump may be installed as an auxiliary to the power pump. It may be used to augment or even supplant the power pump. This is a very desirable safety feature in aircraft. And now we have a simple, selective, power-transmitting hydraulic system that can be applied to many useful tasks. In industry, hydraulically driven and controlled machines are doing a job and doing it smoothly with dependable power and precision. One example, this shaper. Here, the cutting head is actuated by a hydraulic cylinder. The system is designed to provide smooth power on the cutting stroke with fast action on the return stroke. Hydraulics is at work in our daily experience and right underfoot in the hydraulic brakes and drives on our cars. This hydraulic hoist, or the hydraulic jack, with which even Junior can lift a heavy car. Hydraulic control systems are used in all types of aircraft. Where weight and size is of great importance and dependable, precise operation so vital, hydraulics is answering the need. Often the safety of the crew in the airplane will depend upon the ability of the equipment to get the alighting gear up or down quickly. Almost instantaneous operation of powerful diving brakes, wing flaps, and landing flaps against thousands of pounds of air load encountered in flight. Opening, closing, and regulating temperature control devices, synchronized operation of bomb bay doors, often several times the size of a garage door, against tremendous air loads, propeller pitch settings, and engine controls. The majority of the controls used in aircraft are hydraulic. This is made possible only by the use of sound engineering principles coupled with care and precision in every step of manufacturing. From the careful selection of inspected and tested stock, through many steps of constantly checked, precise machining, close, very close inspection, careful assembly, thorough testing and checking, and through meticulous handling in shipping, comes the equipment that gives such satisfactory power transmission systems. Effective and reliable today, in the better days to come, hydraulics will play an important part in making our everyday lives richer and more comfortable.